All right, good morning, folks. We have 1 minute, so I might as well update you on the Pyridine economy, of which there's about 1,000 in circulation at the moment. And as you know, the exam is going to be pretty hard. Usually it's a 4 or longer hour experience to try to emulate what the real world is like. And as such, it's probably worth announcing that for every 5 Pyridine you have, you'll be able to redeem it for a point on any exam. And we'll let you know how much you have at the review session. The TAs will inform you of how much Pyridine you currently have. And as I mentioned before, you can give it to your friends. You can hold it on future classes, give it to future people, or you can buy merchandise with it. All right, so today we're going to talk about the all-important pyridine. And as you remember from lecture number 1, I think it is the most aromatic of the heterocycles. And therefore, based on our rules in lecture number 4, it should therefore be the heterocycle that is least important from the standpoint of ring synthesis, but rather ring substitution is going to be the go-to way of making pyridines a majority of the time. However, I have seen medicinal chemists make pyridines quite often. And of course, if you're going to go into process chemistry and you don't know how to make a pyridine, you're going to be in deep trouble. Often that is the sneakiest and best way to avoid cross-coupling chemistry, is simply to make the pyridine. And that is a consequence of the vast array of condensation chemistry available to the practitioner when they think about making pyridines. So 3 main categories of strategy can be used, and they really are 90% of the time going to be based on condensation, occasionally based on rearrangement, and occasionally based on cycle addition. But I would say in all my years, if I had to say how often I'm recommending rearrangements and cycle additions, is probably 5% or less of the time. It happens on occasion. I'll show you an example of it today. 95% of the time, though, when we're proposing to make a pyridine, we're going to do it through condensation. And if you think about a pyrrole or a furan or a thiophenes, as we talked about before many times, the conceptual equivalent of those is a 1,4-diketone. And when you homologate that by 1 carbon, you end up with a 1,5-diketone, which makes it a little bit easier to understand because 1,5-dicarbonyls are compounds with a more of, as Evans would call it, a consonant relationship between the functional groups. And so they are then amenable to more standard intuitive polar bond disconnections. So if we take a look at the book really quick before we begin to the pyridine synthesis starburst, you'll see that like the pyrroles, you're really relegated into 2 basic areas. On the left-hand side, you see the ones that are not easily categorized, but are easily understood. And then on the right-hand side are the ones that really correspond and trace really well into 1,5-dicarbonyl logic. And we've organized it in this way because it's a lot easier to understand, and it is a sort of pragmatically an easier way to reference and think about how to make such compounds and where you derive your building blocks. So we're not going to cover all of the syntheses of pyridines today, obviously. What we wanted to do for the lecture part is focus on the ones that rise to the level of most often used, most strategically applied, ones I have seen over the past 20 years or so be used the most often in the real world. Rather than inundating you over the head, we have also removed quite a bit of content from the 2019 lecture and replaced it with things that are going to be more useful to you. And also in input into this lecture, a lot of real world consulting problems with all the IP and substituents removed, of course. So let's begin. We've got the prototypical 1,5-dicarbonyl starting material, which correlates to the classic Hantzsch pyridine synthesis. And there are many variations on the theme of Hantzsch. For instance, if you replace this ester group here with something else, that can be a nitrile, for example, that is the famous Goreshi-Thorpe, which we will cover in great detail. If you replace the ester with an N-pyridinium, that is the Crohn-Key synthesis, which we will cover, can be also quite strategic. And of course, 1,5-dicarbonyls are really nice because you can dissect them into simple Michaels and aldols and things like that. So when you disconnect the compound like this, one possible disconnection which makes sense is to go there. That leads you to these two building blocks, and then you can obviously see how this building block can easily be derived by a simple aldol condensation there. So very intuitive, easy condensation chemistry makes up the lion's share of how one thinks about making pyridines. So with that, let's take a look at how in the past industry has capitalized on the Hantzsch to make some very useful compounds, including these two, which for a time, and they may still be for all I know, billion-dollar drugs. So based on the logic we just saw, maybe Sunghan can drive us through a quick synthesis of procardia. What building blocks do we need?
I think we can drive from 1,5-dicarbonyl and maybe can further start from a symmetrical beta-keto ester.
So in practice, all one needs to do is mix those three together, filter, and then collect the money as it's printed. How about this bottom one, Sunghan? Can we use the same logic here too?
Yeah, I think we can also first go from the 1,5-dicarbonyl. Yeah.
So you can do this unsymmetrical, and generally what you're going to do here is simply use that starting material. You'll pre-generate the enamine on this side, and then dump in the aldehyde, and you'll get the aldol followed by the condensation. Now, it's worth noting that if you want to get the pyridine directly instead of the dihydropyridine, you can do so simply by using instead hydroxylamine, which upon loss of water from the hydroxylamine will give you the aromatized compound. So these 1,5-dicarbonyls are quite versatile if you want to add, let's say, substituents at the nitrogen, or just go to the pyridine directly by buying your oxidation state through the use of something like hydroxylamine. Alternatively, in some cases, you may want to make the dihydropyridine and then oxidize it. And you can do that with a variety of different oxidants, ranging from manganese dioxide, DDQ, palladium on carbon, oxygen. There's probably a smaller list of reagents that will not do that aromatization than will do it. So many, many things will easily do that. So based on what we just learned, we should be able to come up with a synthesis of a compound directly out of a consulting problem. This was from about 12 years ago on how to make this compound. So give me some strategies based on what you learned so far. I'm open to any suggestions. Maybe Nathan can start us off here. What would you do? What's the one atom, Nathan, that's going to guide your analysis in this problem? And if Nathan's not available, we'll go straight to Brendan. What atom is going to guide your retrosynthesis here?
Which atom? I mean,
Yep. Give me one atom.
The nitrogen.
Well, that's nothing special about that.
So I guess maybe you could do maybe you can do like a Michael addition with the aryl piece into the pyridine ester and cut that bond.
So you're suggesting this connection like that?
No. The can you do like a conjugate addition into the ester?
Conjugate addition into the ester. Let me 2, 3, 4, 5, 6, and you're suggesting breaking here. And that would lead you to that. So you want to do a conjugate addition followed by D to Q, let's say. Now, do you think you might have any issues with making that reagent?
Yeah, I guess that bromine, I guess that's what we were getting at then. The bromine is kind of the kicker here.
And you may in fact be able to do that. There may be conditions out there, maybe some fancy no-shell work that allows you to make a brominated Grignard reagent like that. And the conjugate addition is a good idea. It should probably give you the right regiochemistry. You may have a problem with some addition here. That could be an issue. And then you'll have to oxidize after you add in. However, what I wanted you to get at the very beginning was this right here, that when you get a problem like this, that bromine or iodine, you see this often in MedChem, they want that there because they want to do diversity exploration off of that position. So it blocks you from doing a lot of things that you normally could immediately suggest. This is a case where it might make sense to think about ring synthesis. And so if we think about ring synthesis, Tao-Wei, what would be the ring synthesis disconnection that you think might be useful based on the numbering of the carbons I've given you? And if Taiwei is not here, then certainly Ellie can help us out.
Yeah, hi, can you hear me? Sorry.
Yep, I can hear you perfect. Yep.
Great. I'm having audio trouble. So I was thinking we could do a 1,5 carbonyl.
And that would come back from what?
Like a conjugate addition.
Great. Certainly. So you could just put those two together and then oxidize, or you could use hydroxylamine and treating that 1,5-dicarbonyl with hydroxylamine in C2 will give you the aromatized compound directly. And this compound is obviously easy to get, and you have no problem with that bromine on the arene. So awesome. Great. Thanks, Ellie.
Phil, so for these cyclization strategies, you presumably have to have an electron withdrawing group either in the 3 or in both in the 3 and 5 positions. So what if you have an electron donating group? Is it more difficult to use such an approach?
It is. So, for instance, it would be much more difficult to do this chemistry if this was, let's say, butyl or some sort of side chain like that. That's correct. Because it would be difficult from the vantage point of that enamine's reactivity, and more importantly, the regiochemistry of whether the enamine goes here or on the other side.
Yeah. So that is what I thought. So basically, would you say that means actually for electron donating groups, that means such approaches are not viable?
They're not as viable and need to be done on a case-by-case basis. So for instance, if this was a T-butyl or a phenyl and you just did it in a stepwise fashion where you made the enolate and then added in where you don't have an ambiguity on which regiochemical outcome you get, then you could still use 1,5-dicarbonyl logic.
Okay, I see. Yeah, thanks.
Great question.
Hey, Phil, can I ask a follow-up for this?
Sure.
So could you do like a Crohnke and have an aldehyde? Is that stable or no?
So if you're going to use a Crohnke on this with the, so a Crohnke would require, let's do the Crohnke disconnection over here. Crohnke would require something like, that, correct?
Yeah.
Chrome-keys usually require some sort of R group here. Haven't seen those with the aldehyde, presumably because they're not so stable and might self-condense.
Okay.
But it's great thinking, Tim, and I will return to you because we're going to be chrome-keying quite a bit in this class today. So keep chrome-key in the back of your head. That's a great way to end up with a substituent C5 equal to H, because that pyridinium will eliminate, leaving just a nothing in its wake. So that's great. All right, how about problem of the day number 1? We need a good synthesis of Baycol, and then we need a good way to think about how we might make this compound with a radial label at that position. So for this, hopefully Alex can help us out.
So I guess using labeled carbon monoxide to get that, so you can clear that whole R group also in that. And bring that back to like, yeah, halogen.
Where does that come from?
So this kind of gets back to what Nick was saying, where you're going to want an electron withdrawing group there. So
Do it. What would be a good electron withdrawing group that would help us with the synthesis?
an ester, I guess. Which I guess some like Barton chemistry to get back to just the halogen, or to
Yeah.
get to the halogen, yeah.
Unsteker, Barton, there's 100 ways of cheaply going from acid to bromine, for example. And
And-
we need to make that.
And then that's just a good 1,5 dicarbonyl motif.
It is a good 1,5 dicarbonyl motif. However, as Nick said before, if I have 2 electron donating substituents, I need to do something on my retrosynthetic arrow before I do what you wanted.
Well, presumably FGI to an ester as
Oxidize
well.
that side, yeah.
Well, if you treat this with 1 equivalent of red Al, it will go once and stop. And then you can treat with methyl iodide and base. And that will give you your methoxy compound. And then this just comes back from Hantzsch. Make sense? Okay, great. How about this one? And I want, at this center, I would like 100% or 95% control of enantioselectivity. And for this one, maybe Nora can opine on what kind of strategy we might be able to use here.
Well, I think the 1,5 dicarbonyl too, so I could start with the cyclohexane dione
Awesome.
and the corresponding Michael acceptor.
Now, what do you want me to put at that nitrogen, Nora? If I just put ammonia, then I need a solution for how I'm going to control enantioselectivity.
Yeah, so I guess if you have the pyridine and then reduce the 4 position, so maybe use the hydroxylamine.
Okay, so that's an interesting suggestion. You're saying, and this may very well work, Nora is saying, let's use some asymmetric hydrogenation technique to go there, correct?
Yeah, so initially I was thinking it might go for the 2 position, but also the 4 position is conjugated with the ketone.
Yeah, maybe. There may be some method out there that lets you do this selectively, but I'm not sure I would bet an organ on it.
Yeah, me neither.
So what they actually did here is just use a simple enamine here, which controls the enantioselectivity to very high levels. And then they treat the intermediate, they never isolate that. They treat that intermediate with ammonia, and it cyclizes to give the product. And this just comes back from the 1,3-dione. And the corresponding alpha beta unsaturated compound. And this chichibabin. So condensation of these two, followed by addition of this Michael acceptor, and then immediate dumping in of ammonia gives out this compound in 95% EE. And that's process scale. Okay. How about this one? This is an interesting natural product made by the Moody group. We're going to disconnect it all the way to the building block you see here. And I want you to try to come up with a way of making this without any cross coupling. So based on what we learned, is there a quick way that you can imagine putting this together? Nick, what do you say?
Well, so presumably you could make the ring from disconnecting back to the aldehyde and
Aldehyde at C6?
yeah, potentially.
And then what? Did that disconnection help you at all? Or you just delayed the answer?
Not really. So
Right.
basically, if you disconnect the oxazole.
Okay, disconnected how? I don't want you to do a cross coupling. So what do you want to do with that oxazole? Because we haven't learned oxazole synthesis yet. So it's unlikely that the answer is going to involve making the oxazole.
I see. Okay.
Here's a hint. If you notice so far, every time someone said a particular strategy to use, it worked always. What was that?
1,5.
That's it. Just like we
That
talked about
seems
in
too
Furans.
obvious.
Well, no, don't try to make it more complicated than it is. When we saw the same thing with 5-membered heterocycles over and over and over again, even in indoles, it worked. You could derive all sorts of new name reactions and known ones just by thinking about 1,4-dicarbonyls. Same thing here for pyridines. It doesn't hurt just to write out what the 1,5-dicarbonyl looks like.
Right, fair enough. I guess then, yeah, you could use the Kroenke synthesis.
And how do we make this compound? You said Kroenke, but I'm going to give you a chance to change that.
So you potentially want to you'd want to condense.
What's the logical disconnection? Yeah, go ahead and tell me what the logical disconnection is for a system like that.
Presumably you'd want to disconnect 3,4.
Perfect.
And do a conjugate.
Yeah, that gets us back to a Bowman rats. I mean, they all have different names, but they're all the same darn thing.
Oh, I see. Yeah. Okay.
Done. No need to worry about oxazoles yet. Stay tuned to after the midterm. All right. Yeah, what do you say?
For the one that we just did,
Yes.
Could you alternatively use just the vinyl ketone and then the hydroxylamine?
Yep. No problem.
Okay, thanks.
Yep.
Phil, another question on that same problem.
Sure, what do you say, Daniel?
Could you cut that oxazole down the middle and just do a condensation with like alanine and ammonia from the aldehyde that's at the 2 position? That's
so if you insist on going down the route of oxazole synthesis, we can do that. And you're suggesting then reacting with some sort of alanine derivative. And this can be NH2 here. You could then couple with your alanine. And I'm pretty sure that's how you make that building block. So you're likely going to need for this array something like that, if you were to do that. And then couple, and then do a Robinson-Gabriel dehydration. But that doesn't really help you. You're still now stuck with making that pyridine, aren't you? So you've identified what we're going to talk about later on in the class on how to make the oxazole, but I would much rather make the oxazole in the form of this simple beta keto ester, easy to make from the corresponding oxazole carboxylate, and then forge my pyridine rather than trying to make this pyridine and then forging an oxazole onto that. Or any derivative that's similar to this in terms of oxidation state would be fine, but it doesn't simplify it in the way that this Bowman-Rat strategy simplifies it. Does that make sense, Daniel? So try to make disconnections which go for the jugular rather than delay your arrival at the target.
Phil, just a logistical question on that. Like that intermediate that you drew in the top right, that beta keto ester, like, is this also amenable to the Cronky? Like if you just condense formaldehyde and instead of starting with that alkyne, start with the pyridinium salt?
So you're saying formaldehyde plus this pyridinium salt and your beta keto ester. Is that right?
Yes.
I mean, if you drew that on a test, I don't see why that would be a problem at all. Sure.
So which would be better, the alkyne or the pyridine?
I would prefer the alkyne just because I know I can make this really easily from a few different routes. One of them would just be the propanoate, or one of them would just be acetylene anion, adding into the corresponding acid chloride here. That seems to me to be really easy.
All right, thanks.
Yep. Great questions, folks. Let's move on to, we used to have a lot more discussion of cycloaddition, but you know, we're trying to teach you things in here you're actually going to use. And the only cycloaddition I've ever seen anyone use in a company is the Boger pyridine synthesis. And the Boger pyridine synthesis goes by way of starting with a ketone. You react it with a catalytic amount of a secondary amine, usually pyrrolidine, giving you the enamine in C2, which then reacts with a triazine, giving you the corresponding pyridine. And we saw an example of this type of chemistry before. Maybe Feng can just quickly tell us what happens in here.
Sure. So first you do simply 4+2, and then you squeeze out the molecule nitrogen with a retro 4+2. And finally, after I think hydrolysis, you squeeze out another pyrrolidine to get your final product.
Awesome. That's exactly right. And the sort of rearrangement strategy, another sort of boutique method of accessing certain types of pyridines, very rarely employed, hardly ever seen anybody do this kind of thing. So that's why we don't spend a lot of time on it. But emblematic of this type of approach of making pyridines, we'll go through a couple of examples, and this is the first of them. This is a problem of the day number 2, and luckily Kelly is going to volunteer for us and tell us what the first step of this reaction is.
Sure. So you can get your ammonia adding into the 5 position of the furan. And then that will push arrows to give you like the enolate form of your acyl group.
And then?
And then you can ring open by breaking the bond between the oxygen and then the carbon attached to nitrogen.
And after a tautomerization, guess what we get?
There's your 1,5-dicarbonyl, and then you can cyclize.
Perfect. The only issue is we've got these 2 choices. We have 1, 2, 3, 4, 5 here or here. And what we see in practice is that this is going to cyclize there to give you that observed product because of the ketone form being dominant rather than the aldehyde.
Do you think if you had an amide instead of that acyl group, you could get a 2-amino pyridine?
So if this was CONH2, I would expect that you would get as a product that. Because amide carbonyls are pretty difficult to add into. So that would probably be my expected product if this was amide. Good question. All right, let's go to a real consulting problem from, I think this was about 8 years ago. So how are we going to approach making this compound? Maybe Simona can help us out. Real problem, real company. How are you going to tell us to make it?
Can you do a Boger synthesis with piperidone and an amino triazine?
That's interesting. So I like the way you're thinking, because you're gonna try to go for the jugular here and put the amino group into that triazine. However, when you do that, you're going to do 2 things. Number 1, change electronics, and number 2, you're going to make it unprecedented. And if you're giving a consulting suggestion, you don't want to give things that have any ambiguity. You want them always to be as close as you possibly can to be organ donating level suggestions where you are positive the stuff is going to work. So if we take your initial suggestion and just put H here, we can pretty much bet a large amount of capital that you're going to get this product. Correct?
Yes.
And now all you have to do is think about ways of getting an amino group there. So how would you conceptualize putting an amino group there? Tell us.
Can you do a Chichibabin?
Now, normally I would say Chichibabin is a forbidden reaction for most people because they don't like boiling sodium amide with things, and the chemoselectivity is going to be very low. But in this case, if your protecting group is something robust, maybe a Bock group, you probably have a good chance of doing that. Are there other suggestions you can give that may be more mild in case the medicinal chemist starts rolling their eyes when you tell them this?
Can you do like a Vilsmeier?
That's a great suggestion. Vilsmeier suffers from a problem of needing to be reacting with a pi excessive heterocycle. Vilsmeier could work if there was some electron donating group on the pyridine. And we see this in exams every year. Don't do Vilsmeier on electron deficient aromatics unless you've got some really strong activating groups on them.
Oh, so can you make the N-oxide?
Oh, that's nice. And then?
react with
Yeah, I'm going to help you. Luckily, you have this little book called The Portable Chemist to Solvent. And there you go. Is that helpful? Which number do you want to do?
6. Wait, no, sorry. 7.
Pyridine oxide on the right-hand side.
Oh.
That's your pyridine oxide substitution.
Oops.
Cheat sheet.
28.
28 looks good. Let's tap on it and see what it says. Oh, that's good. Well, that'll be good. All right, so we go back here to the consulting suggestion and we say to them, well, you can use tosic anhydride, you can use pybrop, whatever you want, and that will get you to NHR, where R can be equal to H, or it can be equal to whatever they want. You could also recommend PLCl3. And the first question you can anticipate the medicinal chemist is going to ask you is say, hey, how do you know the regiochemistry is right? And so my strategy for addressing this is I go to SciFinder with this compound. I only go to SciFinder at the very end, just to make sure that I have the right idea. So I look for how people functionalize here, and I will find on SciFinder that the regiochemistry, you could argue hand waving and say it's probably not going to go here because of the substituent here that might block it. But hand waving is not good for consulting sessions. So you give them literature that shows that it actually only goes here in this 3,4-disubstituted pyridine. And then you're assured that the route you're suggesting to them is going to work. Great, but Simona hit the nail on the head in the first shot. The pyridine synthesis of Boger is definitely the fastest way to get this compound.
So it's sterics controlled in this case?
I think it's steric and probably electronic, both.
Okay.
Slightly more electron deficient and less steric hindrance is why that dimethyl one gives very good precedent for N-oxide chemistry with PLCl3 going to the C2 rather than C6.
Oh, hi, Professor.
Yeah, please just call me Phil. I don't know who Professor is. Go ahead.
I met this problem before that when this kind of compound was treated with PLCl3, the alpha position of the aromatic ring would be deprotonated.
Oh, you're talking about the Bogle-Hyde reaction. Is that right?
I think, I'm not sure about the name.
So you mean this general type of reaction?
Yeah, and it would be deprotonated. Yeah, and from this kind of rearrangement product.
Yeah, you don't have any C2 substituent to worry about, number one. Number two, you don't have to worry about the C4 substituent. It's not.
Yeah, I'm talking about C4.
Yeah, you don't have to worry about that. These conditions are pretty mild and don't involve any kind of, the faster process to happen in this would be activation. Once you activate the N-oxide, the very first thing that's going to happen kinetically is addition into that now very electron deficient species, and then dehydration.
Oh, okay, thank you.
Yeah, it's a good question. All right, so we're going to cover the synthesis of Chantix in this class. It's a billion-dollar drug from Pfizer for smoking cessation. And you may know people who have taken it. It's apparently highly effective. It was invented at Pfizer by a team of remarkable chemists. The lead inventor, Jotham Coe, a legend in the field of medicinal chemistry. He's since retired from Pfizer. But all of this was inspired by a natural product called cytosine. So we're going to take a little journey. We're not going to cover how Chantix is made because that structure is a pyridine and it's not covered until, or quinoxylane, not covered until later in this class, after the midterm. But we will cover the origins of it. And the origins are from this interesting natural product called cytosine. And so to cover this properly, we have to go way back in history, all the way back to the 50s and 60s with the Van Tammelen route to this alkaloid. So what we need help with now, hopefully Nguyen can help us with a key bond that might be good to disconnect. What bond would immediately unravel and get rid of a lot of the complexity that makes this compound difficult?
I would say the C6 and C, sorry, C5 and C7.
And then you're going to try to do something like that.
Yeah.
Okay, it's a reasonable disconnection worth thinking about. Is there another? I noticed you did 5-7, but what if we just go across the ring and do exactly the same thing, and maybe this time pick a bond which is easier to break, like N1?
Yeah.
If we do that, we end up with something which looks maybe a little bit easier. And I've done some oxidation state changes. So this would need to be reduced to, let's say, a mesylate, and then that would
yeah,
right away.
Yeah.
Now look what happens. We get smoothly to problem of the day number 3, which Daniel has gracefully volunteered to help us out with.
Sure. So I think what would happen is the amine would add into that hidden 1,4 enone within the pyridine.
Oh, that's interesting.
And that would kick down and form the negatively charged nitrogen on the pyridine, which would deprotonate one of the acids. And then that would undergo maybe a decarboxylation.
Well, before we do that, is there something else we can do? Notice there's formaldehyde in here.
Yeah, I was thinking the resultant anion from the decarboxylation would attack into that.
Well, you don't need to do a decarboxylation to get that anion.
Okay.
You've got a malonate here, basically. So this is a very acidic position. And when you've got the formaldehyde in here, you can imagine you've got this kind of species in there, which could then cyclize and get you to your product. There's another way of looking at this, which is more likely what happens, but essentially it's degenerate. So Daniel's logic is not incorrect. It just probably in practice is a different order of events. You're probably making that type of intermediate. And that then will react with the very rapidly with that manic intermediate, which will then do what you said, the conjugate addition, but it all leads you to the same product, that after you form this compound, upon continued heating, you get out the cis product. Make sense?
Mm-hmm.
But it's degenerate, so you can, draw a lot of these same intermediates, but all of them bring you to the thermodynamic well of the product. So a beautiful first synthesis by Van Tamelen back in the very early days. Back in 1958, the synthesis was published in JACS. The Pfizer team needed a more modular and rapid solution to this. So the first way they did it, they divided themselves into separate teams and came up with a more modern solution, which would be amenable to analog synthesis. So they took cytosine and they imagined, well, this ring could potentially be reduced And this is a pyridone hiding, which could be unveiled if at the right moment you did an alkylation event here, probably after some sort of hydrogenation, because in the current form, it's geometrically impossible, but strategically that's what they were thinking. So in practice, how do we execute on this? Well, we can take these two bromides, we can do a Stille-Kelly type coupling. Why do you think the Stille-Kelly coupling works so well? We need a organometallic expert, and maybe Carter can help us out with understanding why, when you take these two bromides, you selectively get the heterocoupled product rather than the two of these simply dimerizing with themselves.
I would think that oxidative addition is much easier with the more electron-rich heterocycle.
So you think that it's easier to put a tin here than a tin here?
Yeah.
Well, it actually turns out that you're right that there's a rate difference, but what likely happens is that the oxidative addition will happen into a more electron deficient center. So this, if you remember the haloselectivity discussion we had, if you've got a C2 and a C3 halogen, the C2 relative to a pyridine will react faster than a C3. So you get a very fast formation of that tin. And then this one is sort of sitting around waiting. And once you've got this Stille compound in hand, this organostenane, it then does the coupling to give the heterocoupled product. So the key is to remember there is a rate difference between those two. Great.
Just a quick question, Phil.
Yeah.
So like that pyridine is, yeah, I agree that the two position is more electron deficient, but let's say dark pyridine is a bit different because it has an electron donating group from the oxygen, and also the other pyridine also has the ester group. So like, I mean, like, I don't know, in terms of balances, it's like, it's just doing, I mean, trial and error.
It's not as electron rich as you think. That methoxy group of the C2 position actually doesn't have an enormous electron donating effect, especially, if you think about it, like its meta position of an arene, it's not actually donating directly into that bromide as much as you think. It actually is, has a lot of conjugation with that nitrogen. You can think of it more like an ester or an amide rather than a methoxy type compound on an aromatic. So don't look at a methoxy pyridine like this and think, oh, this thing is now super activated at the 6th position relative to the 2. It's not, because it's tied up in a negotiation with the orbitals of that nitrogen and not really concerned that much about what's going on at C6. So you can't look at it in terms of that.
Okay, thank you.
Yeah, good question. So we've got another reactivity conundrum to sort through, and that is, in this next step, they treat this with benzyl bromide. And we've got potentially 2 nitrogens by which this the benzyl bromide can react. And maybe the logic that we just talked about can help us with understanding where this pyridinium is going to form. So Junchen, where do you think the pyridinium is going to form?
Yeah, so I will choose like and you label A.
Yay, that certainly makes a lot of sense. Great. And any others? Everybody agree with that? Basically, it's all good.
I think it might be B.
Who says it might be B?
Chonghan.
Well, whenever there's a disagreement, we have to take a vote, of course. So who votes for A? I mean, clearly Junchen, several people raised their hand. A lot of people raised their hand. Okay, great. That's good. I'm happy to see that. And then how about B? Anybody besides Sung Han say B?
Can be B because of the yeah, I think it's B.
Okay, so we're roughly I counted around 63 hands for A and about 42 hands for B. About right? Okay. Well, it turns out that the answer is actually B. And that lesson really stems from the fact that when you make a pyridinium salt, the only thing that matters is sterics. That's what you want to remember. So a 2,6-disubstituted pyridine will generally not be very easy to make a pyridinium. Whereas an unsubstituted pyridine, even if it's got an electron withdrawing group, it doesn't matter. It's dictated by sterics. And so the people who said B definitely won out there. So we treat that with benzyl bromide. And then we treat this with sodium dithionate. So what is sodium dithionate, do we think, going to do in this reaction? It's a strange reagent.
It'll oxidize the pyridinium salt.
You could add as a 1,4 nucleophile.
That's how you can view dithionate. And so, Alex, going back to you, does that look like an oxidizing reagent or a reducing reagent?
Reducing.
Reducing. And so what Nick said is likely going to be what's going on here. And so you're going to generate this type of species. Which then just gets protonated in situ to give you the dihydropyridine.
Phil, would you see any reduction of the other pyridine, or do you need the activation from the alkyl group in order for that to go?
If you don't have the activation, it's out. You're out of luck.
Okay.
Not going to happen. So now when we treat this with H2 and platinum, followed by LAH, we get something looking a lot like Van Tamelin's intermediate. And when we treat this with mesyl chloride, triethylamine, followed by toluene and reflux, and H2 palladium, out pops the product. But I need to understand what the mechanism of this is. So maybe Tanner can tell us what step 1 and step 2 and step 3 do. Tanner or Shuang or Debbie. All right, no takers. How about Tim?
Yeah, sure. So the first step will mesylate the primary alcohol.
Next.
And then after that, the toluene will, so the mesylated alcohols will go leaving groups. So you can get cyclization here. So you have the nitrogen kick that out. And then mechanistically, I'm not super sure about that last step, but you have this reduction. So you have to lose the methyl on the methoxy to generate your pyridone.
When you've got the counter ion here, the mesylate that leaves, and you keep heating it, what you can actually do is just that counter ion can just come back in, clip off that methyl, and you get your pyridone directly.
So
and then
just that acidic?
It's pretty reactive.
Yeah, okay.
So that just clips that off, and then that benzyl group comes off with H2 and palladium, and we're done. That was team one's approach to cytosine. And in the back-to-back orglets that Pfizer reported several years ago, we see team two's approach, which is to take a look, this was Jotham's approach, to take a look at this top part of the molecule, this pyridine, as nothing more than an ozonolysis and reductive amination hiding. And that has a dramatic ability to simplify the problem because we can then take advantage of, I forget who it was it Nguyen? It was,
yes.
Yes, Nguyen's 5-7 approach comes back to haunt us. Look at that. Here it is. Are you happy to see this, Nguyen?
Yeah.
Yes, very happy because in 30 seconds, you basically came up with the exact idea that they had. So the way that they make this compound very quickly, let's take a look at how we would unravel this. If we make this compound via the exact disconnection that Nguyen pointed out, it would require something like that and a Heck coupling. Correct? And in practice, the way they achieve this is simply by taking glutaramide, cyclopentyl alcohol, and then the X that they use here is a diphenyl phosphate, which is a fantastic alternative to triflates when you're dealing with amides. They're stable, crystalline, columnable compounds that have roughly equivalent activity to a triflate in palladium couplings. Any questions?
I have just one question regarding the previous synthesis. When it comes to the relatively stereochemistry of the two substituents on the pyridine ring, how did they control the relative stereochemistry in the hydrogenation or like in the van-Tamerlane synthesis?
Yeah, so the bentamalin is controlled by thermodynamics. You want those substituents equatorial, and then the hydrogenation, once the first hydrogenation goes, then the second one is going to go away from that other ring, so dictated by steric, so you get the cis as the major product.
Oh yeah, right.
Great question. Any other questions? All right. Let's move on to putting this all together, and a little fun activity to do in these problems of the day to make them more realistic to the real world is to put the proviso that we don't want any metals. And you see this as often is, you're not going to have an issue or need to hire a consultant or ask for help if you can use metals to make a very simple compound like this. However, if this is a substructure of something for which you simply cannot do metal-based chemistry, then it becomes really important that you have other methods at your disposal. So we will introduce a different reaction we haven't talked about as a useful way of making this type of compound. But I'll leave it open to maybe Tiffany to start us off on maybe any thoughts that she might have. Or A.
For this first one, I was thinking of 1,5 dark carbonyl disconnection.
Okay. How do we make that?
I guess can you do it by just conjugate addition?
The only questionable thing, and it's probably going to be okay, the only questionable thing would be whether or not you're going to get the right regiochemistry in a system like this. It could certainly work. I mean, on a test, I'm not sure that we could necessarily take points off. And it's clear that when you have this intermediate, you could get to the desired pyridine. There's another type of reaction, though, that you might want to think about. And the first sort of lesson from this is that if you have a C2 pyridine with a 3 or 5 alkyl substituent, it's possible to selectively oxidize that methyl group, not touching that C3 or C5 alkyl position. You can do that by either the Boger type reaction. You can also do it with selenium dioxide, and you will not touch generally, you will not touch the C3 or C5 position. Now, with this dialkyl compound at hand, you can imagine it could possibly arise from this dihydropyran, which then is a signaling element for a reaction we have not talked about, a Thiophenes. It's the other of the two cycloadditions that I've ever seen anybody care about in companies. And so this takes place by a simple inverse electron demand Diels-Alder cyclization by loss of water, and then, or loss of the OR. This could be ethoxy, for example. Treating that with hydroxylamine gets you to this compound, and then selective oxidation gives you the product. Thiophenes can be a pretty useful way of making a variety of different compounds. So for example, if you wanted to make a compound like that, it becomes fairly easy to imagine that it could arise simply from the coupling of a product you probably made when you were an undergraduate in the lab, benzaldehyde and cyclohexanone exhausted aldol, plus ethyl vinyl ether, and you're done. So looking for the Thiophenes can be quite helpful in many cases. You can use the same logic, for example, to make a compound like this. And I'll let you figure that one out, jot it down yourself, but same type of logic, just using a alpha beta unsaturated ketone and ethyl vinyl ether. Great. Now we talked about one way of doing problem of the day number B conceptually, but there's another way to do problem of the day letter B using a different type of reaction of a category we said is rarely employed. So who has an idea for B? Notice I said no metals, so there will be no metathesis for this product.
Well, I still have a question about A.
Yeah.
Since it is a reverse Diels-Alder reaction, which the dienophile is electron donating,
yes,
why do we need to convert the CO2H to methyl group?
Oh, I see. So you're saying why not just use here an ester instead?
Yeah.
You could probably do that. I'm not sure if that microacceptor is so stable, but you could certainly propose it on a test. This is what they did in literature, so I can't sort of invent what I wanted them to do. But you certainly, I think you could propose that. It's reasonable. That kind of compound is probably not so stable, but neither is methylvinyl ketone. But certainly, if you were going to propose it on a test, we could not mark that wrong. Great suggestion. So to be clear, the things that are kind of not literature precedented in terms of the exact example are everything in the consulting corner of this class. So those are real world suggestions I've given over the years, but they don't have a basis in something that you can find on SciFinder. They're just logical. But the problems of the day, unless otherwise notated, are actual things you can find in SciFinder. Okay, how about B? We haven't heard from Camille. Maybe Camille has got an idea on this one.
Is there another cycloaddition you could do here?
So if we wanted to use, let's say, a like a Thiophenes type.
That's the one we just did, right?
Yep, the one we just did.
Yeah.
And if we sort of redraw this, So take that and then do the conjugate addition and then cyclize. Yeah, I don't see any reason why that wouldn't work. TAs, do you like that example? It's reasonable? Great. Thanks, Camille. Another way to disconnect this would be through a reaction we haven't talked about, but serves as a good demonstration of it, which is the Chiamensen-Denset rearrangement, which basically looks at pyridines like this as arising from ring expansions of pyrols. So if you take this and you treat this with chloroform and base, usually KOH, you'll get a carbene formation, dichlorocyclopropionation, ring expansion to give you selectively this compound. It reacts with the more electron donating pi system of this one rather than this one. And this is then simply derived from using standard Palnor chemistry. So that plus this glycine derived aldehyde.
Once you do the Chiamensen-Denset, how would you get rid of the chloro?
Oh, palladium on carbon should be fine. Yep.
Okay.
There's no other offensive functionality here, so you should be fine. How about stone for this strange pyridinium species?
1,5-dicarbonyl.
Right. And then you would just dump in your amine and you would get the product. That sounds great. There's another way of making these strange pyridinium compounds, and that is via the zinc-A reaction, which I just want to remind you we covered already, I think in lecture 2 or 3, lecture 2. But zinc-A could be an option to think about as well. But in this case, I would favor exactly what you said, Stone, which would be just make the 1,5-dicarbonyl and add in the amine. All right. How about D, which gets us into a different reaction we only mentioned briefly at the beginning. And let's start way back at the beginning. How about Sung-Han? Any suggestions for D? Let's label the carbons to make it easy for you to shout out a suggestion.
I think I will cut 3, 4, and 6 and nitrogen.
Brilliant. That is perfect. Okay, so Sung-Han is being showered in Doge today. Perfect. Cut right through the middle. Pretty easy to see that. Let's move on to Nathan for problem E. Any thoughts on this one? This one's a little bit more complicated, but just some general thoughts on how you might do it will probably get us to the answer. Oh, Nathan's not here today. So Brendan. Give me this. Would you think condensation, rearrangement, or cycloaddition? And we'll take it from there.
Not condensation.
Not condensation. Okay, that's very good. And you're left with rearrangement and cycloaddition.
I guess like the cycloaddition would make a little more sense, probably.
Another great Boger synthesis, not the one that I showed you before, but rather the use of inverse electron demand Diels-Alder reactions of N-sulfonyl azodines. These are really powerful. They're really easy to make. And it gives rise to the exact ethoxy group that you want. This is easily made. Dump those together, and you get out the product very quickly. Can't think of a better, faster way to make that compound. And your signaling element for it, at least for me, is sort of that group there and that group there. And yeah, great. How about F? F is one that I don't necessarily need you to give me the retrosynthesis of Tau, but I want you to just tell me what you think about when you see a group like that. What comes to your head as, oh,
I
I
think maybe we need to deprotonate the 3 position and use formaldehyde and use DMF to react with it to add a CHO group here.
So you want to go from here, do some substitution chemistry on that.
Yeah.
The only issue I would have is, you know, the relative directing groupability of that, the ester versus the chloride. You might be fine. Maybe the chloride does the directing chemistry there. That's possible. Is there something that should speak to your heart when you see 2 carbons that are adjacent to each other, one with an aldehyde and one with a chloro? That a type of chemistry we've talked about before. As I remember, Nora was the expert of this chemistry.
Would you start with the ketone and subject it to Vilsmeier?
Aha, that's what I was looking for. Vilsmeier to the rescue. It's going to come to the rescue a lot today. So all one needs to do. Can you imagine it's this easy? Just take that and treat it with a Vilsmeier reagent. Can you imagine it's that easy? That's pretty crazy. How does it work? What is going on here? Well, Vilsmeier is going to go absolutely crazy with this compound and formulate everywhere it can. So we're going to do canonical Vilsmeier of the type we talked about in, I forget what lecture number it was, where we covered Vilsmeier in exhaustive detail. We're going to get that intermediate. And all that you have to do now is to close the ring, lose dimethylamine, not once, but twice, and upon workup, you get the product. I mean, that is so ridiculously easy. It's so easy and beautiful and cheap.
Hey Phil, for that aldehyde in F on that pyridine with the 2 ester, is that still electron rich enough to react with Vilsmeier?
Sorry, which one? Sorry?
So F, the molecule we're working on,
Oh, yes, okay.
is that reactive enough to work with Vilsmeier?
Well, F is the product of the Vilsmeier.
Yeah, but okay, so if we did the intermediate that you drew where we were talking about regioselectivity of the aldehyde.
You're asking attack this way or the other way?
Oh no, sorry. Above that first retrosynthetic arrow.
Oh, here.
Is that electron rich enough for Vilsmeier?
You mean, could you use this strategy to make Vilsmeier, to make it using Vilsmeier?
I just remember that you had said that pyridines are pi excessive and you need pi excessive systems for Vilsmeier.
Oh, yeah. If you wanted to do formulation on this with Vilsmeier, you couldn't. I think the suggestion we had from Taiwei was an actual lithiation event.
I see. Okay, thank you.
No, Vilsmeier directly. Don't do Vilsmeiers on electron withdrawn systems. Don't do that. We see it every year. Don't do it. Do Vilsmeier on indole. Do it on pyrrole. Do it on maybe an aminopyridine. There might be some literature precedent for that. Certain types of aminopyridine, perhaps. It's probably known. But avoid doing Vilsmeier on a pyridine. Use Vilsmeier to make a pyridine. All right.
Is this likely? Is this likely to work if you have if you had the ester in the 5 position instead?
You mean if
the
ester was here?
Right. If you were to do the same Vilsmeier approach, it should work, right?
I think so. Yeah, I think so. I could be wrong on that, but yeah, I don't see you violating any rules there. I think that's reasonable. But we can check. Yeah, we can make sure.
Thanks.
Yeah, thanks, Nick. Let's get to some real world consulting problems. It looks like based on the time we've got today, we may only get to the consulting problems and you may have to review the 2019 lecture on your own. But that's, I guess, the price we pay for going nice and slow and making sure everyone's happy with the answer. So this is new content. Let's take a look at this exact problem from the archives. How are we going to put this together? Now that all the methods you've learned so far, you should be an expert. This should be no problem. And maybe Ellie can guide us through some of her thoughts when confronted with this problem on a job interview.
Okay, so I feel like you could do the 1,5-dicarbonyl.
Okay, let's do that. See, you know, if you're in the job interview, you just bought yourself time by saying that answer. While I'm drawing this, Ellie, why don't you tell us why you didn't do cross-coupling chemistry?
Because this isn't the lecture for that.
No, come on.
There's the bromine there, so
Great.
we have some issues with that.
Okay, that leads us back to the intermediate we see there, which is fabulous. Now, how do we make that?
You could just do like a conjugate addition from the.
Okay. Now you see, you bought yourself time. However, the conjugate addition. Now I'm the job interviewer, and I'm going to say, hey, Ellie, don't you think there's an issue with regards to the regioselectivity of your conjugate addition? What is going to be your answer to that if you want this job? The interviewer is asking you, why is it not going here versus the beta substitution, which should slow down the conjugate addition, thereby derailing your idea. What's your response?
I'm not sure.
Well, all you need to do is go back and think to yourself, okay, the way I'm going to do it, you put me on the spot, I'm going to think about, oh, he or she is right. That is a good point. That may be a problem. In order to avoid a regiochemical quagmire, I need to make sure this carbon-carbon bond is there from the beginning. And then I can recall, well, the way of making sure of that would simply be, let's just draw a triple bond for an identical riff on your original idea, Ellie, would just be that plus ethyl vinyl ether. Now I know I've got that carbon-carbon bond in place. Nobody can complain about regioselectivity. I know ethyl vinyl ether through a Chichibabin is definitely going to go delta minus here, delta plus here. I know my regiochemistry is right, and then I can do the exact same thing that you suggested. Now you bought the time by saying 1,5-dicarbonyl, and while you're drawing it out, you can already begin thinking about these problems that are downstream. See the advantage of that?
Yeah.
So you probably got the job. All right, great. Let's move on to some more consulting problems. This time, no metals. This is new content. You can't find it on YouTube. How are we going to make these compounds? So hopefully, let's go back to Alex. No metals for any of these. What are some thoughts on how you would navigate this maze of trouble with this pyridine?
I guess I would start with drawing the 1,5-dicarbonyl just to think about that.
Okay. You're getting close. Now what? Let me help you. With these bonds, you can give me my next disconnection.
I'm not seeing a clear difference between wanting to break it 2, 3, or 3, 4.
Awesome. That's great.
Yeah.
So if we take the 2-3 disconnection, we can imagine using Tim's favorite reaction, the Crohnke. And if we take the 3-4 disconnection, we can imagine doing it in the opposite mode. Both of which are fine. So, I mean, look, somebody puts it up in the job interview and you come up with that, you know, I don't see how you don't get the job. That's pretty quick. Fantastic.
There is no way to control stereochemistry.
Aha, the stereochemical problem. Well, that basically comes from you're going to need access to that, which all you have to do is you can probably get that through a reduction sequence and then desymmetrization of that by addition, let's say, of one equivalent of methyl magnesium bromide to get that, or one equivalent of vinyl magnesium bromide to get that. That's one way. Another way you could possibly think about doing this, by the way, since you mentioned it, Nick, I'll just mention it here. You could imagine taking this, making the monoanion. We're going to see an example of very similar chemistry later on in the class. We wouldn't need any metal. We would take the dichloropyridine and do an SNAR reaction once, and then do a decarboxylation to get the thermodynamic product. That's something else you could have proposed. That would have been reasonable.
So could we do something that what we did in POD3?
What did we do in POD3?
The benzylamine conjugation, except just do a carbon homologation.
Oh, you want to start, so Tim wants to start breaking up this ring system.
Yeah, I don't want to touch the pyridine.
Yeah, you could think about doing things like that, but in terms of convergency, it's far more simple to start with building blocks like this that are widely available and methods are known to control stereochemistry, and then cut it right down the middle to the degree you can. So either breaking this bond here, or the ones we break in the subsequent Alex manipulations 2, 3, and 3, 4 are also relatively convergent. So we're aiming for convergency here. If you start breaking up in this ring system, you're going to have likely a longer synthesis.
Phil, could you try doing the Stetter reaction?
Well, for a 1,5-dicarbonyl, you're going to have issues with Stetter.
Oh, sorry. Yeah.
So that's a good point. Remember, Stetter, folks, is umpole chemistry, which means you're looking at dissonant heterocycles, which means you're looking at 5-membered rings. When you get into 6-member rings, you're looking into 1,5-dicarbonyl chemistry, which is consonant relationships, which means polar bond disconnections, which means aldols and Michaels. Great question. All right, let's look at this other consulting problem. How are we going to make this? No metals allowed. Gee, that's this one looks really rough. We need we'll need maybe multiple people to help us out with this one. I don't know what to do. Maybe Simona, and she can recruit someone else with her. I don't know how to solve this problem.
Can you do a Chiaminsin densite and trace back to the parole? And then disconnect that from like a NOR or a Hantzsch that we did a few lectures ago.
I think that's a phenomenal idea. I think the only potential issue you're going to have is the question of regiochemistry, which in this case, because these groups are kind of electron deficient, you probably have a good case to be made that the carbene is going to go onto that carbon. So that looks really great. That looks awesome, Simona. But I'm going to up the ante because you got that so quickly. I'm going to give you an opportunity for some more Dogecoins. Let's change the problem. Now give me the answer. And you can't use metals, so I don't want to hear about how you're going to cross-couple some CF3 zinc species with a chloride.
Can you do like a Chichibabin? Are the electronics right there?
Something like this?
Yeah.
It might work. I don't know how stable or accessible this thing is. I'm not sure if you can get that compound in hand, but I mean, for a sort of paper idea, it's reasonable. Let's take a step back, however, and look at Simona's near identical. So the precursor to, let's do the precursor to this. So how are you going to make that? You're going to make that from, whoa, you've got it already here. Intermediate A. That comes from intermediate A, right? Now, if you take intermediate A and you react it with this compound, this is known as a vinamidinium reagent, derived from my favorite concoction, which is Vilsmeier. You just dump and stir those together, and you're going to get out that, where R is equal to, look at all the things we can do. Bromine, iodine, CF3, phenyl, phthalimide, N-phthalimide, nitro. Any of those things are fine. Look how powerful this is. It's crazy. And you're done. Where does the where does this thing come from? All you need to do is start off with your alpha substituted acetic acid. Treat this with DMF and POCl3, our favorite Vilsmeier conditions, and you go through the intermediacy of something like this. And you can imagine all one needs to do now is a Furan-like mechanism where I think you lose carbon monoxide and Cl, but you could imagine if there was some hydrolysis that took place, you could get slosh of CO2. But that's how you make the vinamidinium intermediate, which then reacts with this ketone to give you an annulation event directly to anything you want, CF3, chloro, nitro, whatever. How cool is that? Great.
This is a great trick. Can you
Great
have
trick,
an
isn't it?
electron?
Yeah. What do you say, Nick?
Can you have R as an electron donating group as well, or better be electron drawing?
N-phthalimide is as close as you can get on that one. I don't know of any examples of electron donating groups like methoxy, for example.
Okay. Okay. Yeah. Thanks.
Yep. We only have 2 minutes left. And so I think the best way to end the class is probably to do new content. You can find this on YouTube. You can find this and this on YouTube. And this is an appendix that you can find in the book. So in the final 2 minutes, let's do something new that you can't find online. And that is this HDAC inhibitor from AstraZeneca in OPRD. And so for this one, we need some general thoughts. However fast we can get through this is when the class will end. So Junchen, maybe you can take us home here and tell us some thoughts on a disconnection strategy which might be useful.
Yeah,
you're allowed to use metals if you want.
Oh, I'm allowed. Okay.
You're allowed if you want them. You don't need them, but if you want them.
Yeah, so still using the 1,5-dicarbonyl strategy, breaks the pyridine. And cyanide serves as a very nice conjugate acceptor. Oh, yeah.
And how do we make this?
Mm. Yeah.
We're really close.
Yes.
All you have to do, look, Jin Chen, I'm gonna make it easy. All you have to do is tell me a bond.
Oh yeah, you label that. So break this for C4 and C5. Oh, sorry, C3 and C4.
C3 and C4 is going to give us essentially this compound. Wherein you can imagine addition here and then cyclization with ammonia. Now, in practice, they do not do this. What they do is bring this back down to the corresponding chloro, cyano, and they do Suzuki. What I've just drawn is perfectly acceptable for a test or consulting suggestion. I wonder why the process chemists didn't actually do that by themselves. But what they did is a Suzuki, and then that can be brought back to the exact same disconnection as Junchen. But what we're going to put here instead of the AR is use acetamide and then POCl3. The other way to make this compound, if you don't like that, would be to start from here. Do a reductive amination. And how do you make this compound? I mean, this is just gorgeous. Look at what we're going to do. I'm going to take malonyl dinitrile. I'm going to treat it with acetaldehyde. And then I'm going to treat it with PLCl3 and DMF, our favorite Vilsmeier concoction. And that gives you the product. I think it's probably worthwhile to draw out how this happens before we depart for the day, because it's so darn pretty. So the initial adduct you get is that. When you then treat that with PLCl3 and DMF, you get that. And in the same pot, watch what happens. You are going to get chloride, and this is a really important step to remember. When we get to naphthyridines, you're going to see this again. Chloride adds into the nitrile, doesn't matter which one. That then adds in here, and out pops after you work up the reaction. Out pops the formation of this pyridine after loss of dimethylamine twice. Do you see that? Vilsmeier can be confusing at the outset. Practice Vilsmeier. Understand what it does to acidic positions like this, which is a very acidic position. Remember, we saw this before in the Gawal Thiophenes synthesis, where you could treat this with S8, and it went there. This is a very acidic position. Treat that with Vilsmeier, you get exhaustive formulation. And then the chloride comes in very sneakily. Oh, how do I get rid of that keyboard? Okay. Comes in very sneakily to one of these nitriles, attacks it, which then condenses close. You're going to see this again, this exact maneuver, when we talk about naphthyridine. So remember it. All right. So we ended a little late. Sorry for that. Any questions?
Are there any?
Yeah,
Oh, sorry, go.
Okay. Well,
Yeah, I just had a question. Would doing like a Guareschi-Thorpe be a bad idea? Because you'd end up with like some oxygenation where you need to add in that large, like R group.
Well, Guareschi-Thorpe would require something really strange. You would need something like this. And I'm not sure I want to handle a trialdehyde like that.
Are there any potentially issues with regioselectivity when you bring in many components like this into one mixture?
Well, you made it impossible to worry about regiochemistry because I have everything is symmetrical. So what regiochemical problem would I have in this case, Nick?
So what I mean is at the top when you have the cyano ketone condensing onto the aldehyde at the top right.
Oh, Junchen's disconnection. Yeah.
Yeah.
That's a good question. So in the cyclodehydration event to make the pyridine, the ketones react faster than the nitriles. That's what you need to remember.
I see. Okay. And you wouldn't, yeah, so you would definitely condense onto aldehyde, for example, you wouldn't do any.
Yes. And if you have two nitriles, you'll get an aminopyridine.
I see. Okay. Yeah. Thanks.
Yep.
Wait, I'm sorry to belabor this, but for what I was saying before, why can you start with the tertiary amine already installed so that you don't have the aldehyde there? Like I was picturing it with the full R group on that side.
Well, that's perfect. That's exactly what we do. That's what they use. That's your Guarashi-Thorpe. Perfect. Yes, exactly right. So this A plus B is a Guarashi-Thorpe, and that's what they do. Brilliant. Perfect. Exactly right. You see that, Alex?
Okay, yeah.
Yep, you're good. Question from the outside before we depart.
Very quick one. Someone wants to know the name of the Vilsmeier book you took from consulting.
The name of the Vilsmeier book we took from consulting. I've got it in my office. It's Vilsmeier Reagent and Organic Synthesis, I believe is the name. You can probably get it on Amazon, but I'll find it in my office and we'll scan the cover for Max and they'll send it to you. So yeah. All right, great folks. So we have a all new lecture coming on Friday. Where we will talk about our first fused heterocycles. So everything we've learned in the past 7 lectures you'll need for this Friday. It's going to be an exciting one. So see you then. Thanks, everyone.